This P1 video is for Redshift, Hubble, evidence of the Big Bang, and the fate of the universe. So the first thing to deal with is what is Redshift? Well, it's an example of the Doppler effect, but specific to light waves. The Doppler effect can apply to any waves, and it's the change in wavelength and frequency when the source of the waves is moving relative to the observer. So a common example is a car driving towards you sounds higher pitched, and a car driving away from you sounds lower pitched. So you're all familiar, hopefully, with this example, and it sounds something like this. As the car is coming towards you, you have this kind of effect, and as the car goes past, the pitch drops. Okay, so the car went past the person, the pitch dropped. That's the Doppler effect. Okay, and that's the Doppler effect in sound. But the Doppler effect equally well applies to light, and for the purposes of studying the universe, that's the one we're interested in, because the only information we can get from distant sources like stars in other galaxies is from the light that they emit. Okay, so, like we said, the car moving towards you has a higher frequency or pitch, and that means a shorter wavelength, and the car moving away from you, the sound has a lower frequency or pitch, and therefore a longer wavelength. And this effect applies to all waves. So, if we look at it in the context of a star, there's our star. We have two observers, one either side, who are not moving relative to the star. So the star is stationary as far as they're concerned. And the star gives out some light, there's the waves, and the wavelength of the light is the same for both observers because the star is stationary. And it looks the colour of the star, yellow in this case. So what do we get if we have a star that's moving? Well, if we have this star here, we have observer number 3. The star is clearly moving away from observer number 3, and the star is clearly moving towards observer number 4. And what happens is, as the star is moving, the waves are being emitted. So that causes the waves to stretch behind the star. So the observer that sees the star moving away sees a longer wavelength, just like they did with the car moving away, the wavelength was longer. And the same thing with the observer that sees the star moving towards them. There, the star is catching up with the wave as it's being given out, so the wavelength is squashed, and you get a shorter wavelength. And that corresponds to a blue colour. So what does that look like on the spectrum? Well, here's the visible spectrum with the wavelength represented. So on the left-hand side down here we have the long wavelength red end of the spectrum, and on the right-hand side we have the sort of blue-purple short wavelength end of the visible spectrum. Do remember this spectrum keeps going as well, right? So past the red we have infrared, and past the violet we have ultraviolet. Okay, so the observers 1 and 2 see the normal yellow colour of the star. Observer 3 sees the wavelength stretched, and so he sees the star redshifted. Okay? The light from the star is shifted towards the red end of the spectrum. What that really means is that the wavelength is longer. Okay, and similarly, observer 4 sees the wavelength shortened, and that's the blue end of the spectrum. So the observer 4, with the star moving towards them, sees a shorter wavelength. And what happens if we change the speed of the movement of the star is the next question. Well, that star was moving at a certain speed. If we make the star move more slowly, then as you might expect, there's less shift in the wavelength. Okay, observers 1 and 2 remain unchanged, and now we have observer 3 with the star moving more slowly. Well, it's shifted still towards the red end of the spectrum. It's still redshifted, but it hasn't shifted as far. The wavelength is not stretched as much, and the same thing for observer 4, where the star is moving towards observer 4. It's shifted towards the blue end of the spectrum, but not as much as it had before. So, in summary, light that from a star that's moving away from you will be redshifted. The faster it's moving, the more redshift there will be, so the longer the wavelength of the light will be. And for a star that's moving towards you, the light will be what we call blue shifted, with a shorter wavelength, and the faster the star is moving, the shorter the wavelength will be. So how do we use this to interpret the motion of stars? Well, very usefully, every star has a pattern of lines in its spectrum. So the image on the left here is the spectrum of the sun. It's what you would get if you put the light from a sun through something we call a spectrometer. Okay, and the little dark lines are present because of the elements in the sun's atmosphere. And every element has a pattern of these dark lines. It's like a fingerprint for the element. And they're in very specific places in the spectrum. And as I said, we use this instrument called a spectrometer, which acts like a prism to split the light up, okay, into its spectrum, and we can see these dark lines. Now, the useful thing is we know exactly where they're supposed to be depending on which element it is. So if we look at the individual lines for an individual element, okay, and we measure this in the lab by putting some light through a cloud of gas made of the element, okay. So this particular element here, doesn't matter which one it is, has two sort of dark lines in the purple region of the spectrum, one dark line in this sort of blue part of the spectrum, just verging on the green, a set of three here between green and yellow, two in the orange and one in the red. And that's what we see when we look at this element in the laboratory. We shine a light through it with every colour present. It absorbs these particular colours. So then if we looked at if we found the same element in the atmosphere of a star by looking at the light from it, we would see the lines. But in this case, the lines are all there, same spacing, but they've all shifted a tiny bit towards this red end of the spectrum, just like we talked about before. Okay, so this star, the light is redshifted. The lines have moved towards this red end. That means that this star in this galaxy is moving away from us. Okay, when we talk about galaxies moving away from us, we're really talking about looking at individual stars within that galaxy and looking at the shift of those stars. But really the whole galaxy, if we do it for several stars within the galaxy, we find the same results. All those stars have a similar redshift. That means the galaxy itself is moving away. And if we were to find light from a star where the lines had shifted the other way, so this time again they've shifted towards the blue end of the spectrum, that means that the star in question is moving towards us. Okay, we call that blue shift. So in this case, if we found stars in a distant galaxy where they were blue shifted, that would mean the galaxy is moving towards us. So that's what redshift is, and the information it gives us is literally how fast the galaxy is moving and whether it's moving towards us or away from us. The more redshifted it is, the faster it's moving away. The more blue shifted it is, the faster it's moving towards us. Okay, so before we go on and talk about how that gives us evidence for the Big Bang, let's just make sure we're happy with blue shift and red shift. So using what we've just talked about, I've given you here a little question to do, which is to look at the spectrum for this stationary source in the lab here, which is the top one, and then there are spectra from three galaxies, so stars within three different galaxies, Galaxy A, Galaxy B and Galaxy C, and your task is to describe in as much detail as you can what the motion of those galaxies is by comparing each one to the stationary source. Okay, so pause the video and then in as much detail as you can explain how you know what the motion of the galaxy is by comparing the spectra, and we'll go through the answers in a second. Okay, so let's have a look at the answers then. And you could try and tackle them all at once, but really two of them kind of go together and one is separate when you look at it. So I've just put the spectra in the top left corner so we've got some space. Now the question was describe and explain the motion of these galaxies in as much detail as you can by looking at the spectra. So there are various levels at which we can do this, and we look at Galaxy A and C to start with. And the reason we look at Galaxy A and C is if we look compared to the lab source, both Galaxy A and Galaxy C have redshift. Okay, the lines in the spectrum are shifted towards the red end. It looks almost as if Galaxy C's got something else going on, because the sort of big dark line in the lab source has kind of turned into two lines. But if you look at the spacing, that's the critical thing. You can see the spacing of the lines matches. And in fact, we've lost the right two lines off the lab source because they've been shifted out of the visible spectrum in the Galaxy C. So those would be somewhere down here in the infrared in Galaxy C. So looking at Galaxy A and C together, well, a description only would tell me, well, Galaxy A is moving away from us, but not as fast as Galaxy C. That's describing the motion of the galaxies. They're both moving away because they're both redshifted. But to properly explain it, we need to link that motion to the redshift. In other words, explain how the redshift shows us that those galaxies are moving. So, both Galaxy A and C show redshift. Any redshifted object must be moving away from us, but Galaxy C shows much more redshift, so is moving away faster. Okay, now, the reason I've underlined and highlighted the word so in here is because there are various words that kind of force you into making an explanation. Things like because, so, therefore. We'll talk in a separate video about these words, but the basic idea is that if you include one, it's quite difficult to not explain something. A description is just this first sentence here, but if you include the word so, you can't really help but explain something. Okay, so now looking at Galaxy B, well, there's a very slight blue shift in Galaxy B. Okay, it's very small. It's only moved a very small amount towards the blue end of the spectrum. So Galaxy B is moving towards us. There's our description. Description and explanation. Well, Galaxy B shows a blue shift. Any blue shifted object must be moving towards us, so Galaxy B must be moving towards us, linking what you see in the spectrum to the motion of the galaxy. And that's very similar to the description explanation we've got over here for A and C. If you wanted to include even more detail, we could compare the speeds of B with the other two, because even though Galaxy B is blue shifted, we can still see that the amount of blue shift is small compared to the amount of redshift even for Galaxy A. So that means that yes, Galaxy B is moving towards us, but it's moving towards us faster than Galaxy A is moving away from us. That's what the amount of shift tells us. Now, as we're going to talk about in a second, the evidence for the expansion of the universe is that distant galaxies are moving away from us. So what this probably tells us, though you didn't have the information to answer this given the question, was that Galaxy B is probably quite close by to us and is part of our local group of galaxies, our local cluster. Okay, because of that, gravity is attracting it towards us, and it may be the case that the local galaxies, the ones that are nearby, are able to move towards us and therefore do have a slight blue shift. But when we look at the Hubble data and the galaxies we'll see in a second, the distant ones are uniformly moving away from us. So, Galaxy B probably close by. Okay, so what is the evidence for the Big Bang and how does it link? Well, we just talked a lot about redshift. And what we see when we look at the redshift of distant galaxies is that all of them are redshifted, first of all, which suggests that the whole universe is expanding. We'll talk about why we think universe expansion rather than just the galaxies moving through space in a second. And the second, more detailed piece of information is that the further away the galaxies are, the more redshift they exhibit, and therefore the faster they're moving. And that pattern is exactly what you would see in an explosion. Right, fragments of anything coming out of an explosion, the fragments that are further away from the explosion are moving faster. So this speed increasing, distance increasing relationship is exactly what you see in explosions. So it's very strong support for the idea of a Big Bang. The second piece of evidence doesn't really prove the existence of the Big Bang on its own, but it certainly doesn't contradict it. It doesn't go against the idea that the oldest stars we can observe seem to be about 12,000 million years old. Okay, now that in itself is not particularly useful, except for the fact that the Big Bang theory tells us, when we look at it, that the universe should have formed about 14,000 million years ago. And the basic way it does that is by looking at where the galaxies are now, looking at how fast they're moving, and kind of running the film of these galaxies backwards, and that will then allow us to calculate when they were all kind of on top of each other, which should have been the moment of the Big Bang. And if you do that, you get a figure of about 14,000 million years. It's probably closer to 13.8. It keeps getting revised as we get better and better data. But we'd be in trouble if the oldest stars were older than that. But they're not, so that it fits with the idea of the universe being about this 14,000 million years old figure. The third piece of evidence is the composition of early stars. If you remember from looking at light coming from distant stars, the further away we look, the further back in time we're looking. Okay, so light from our sun takes about 8 minutes to reach us. Light from our nearest star that's not the sun, about 4.2 years. If we look at a star in a very, very distant galaxy, we're talking billions of years old. And if we look at very distant stars, those first ones that we talked about in the previous piece of evidence, we find that their chemical composition, which we can tell by looking at the light from them, is pretty much exactly what you'd expect from the Big Bang. It's about 3/4 hydrogen, 1/4 helium, and nothing else. So the Big Bang predicts this proportion. The Big Bang theory predicts this proportion, and so the fact that we observe this proportion of hydrogen and helium is very strong support for the Big Bang. If we observed a different proportion of hydrogen and helium, or other elements in there, it would suggest that the Big Bang theory wasn't correct. Okay. And the final piece of evidence, which is one that you're not necessarily supposed to know a lot about, but it is a piece of evidence, so we're going to talk about it here, is something called the cosmic microwave background. And the basic idea behind this is that during the Big Bang, a lot of radiation was created, a lot of light, and it's still there. And because the Big Bang created the entire universe, this light is everywhere in our current universe, and it's travelling in every direction. So no matter which direction we look in the sky, we should be able to detect this radiation. Now, it was very hot in the Big Bang, and this radiation was very high energy, so we're talking gamma rays, the very short wavelength, high frequency end of the spectrum. But now, because of the expansion of the universe, this radiation has been redshifted down into the microwave part of the spectrum. So we can't see it, but we can detect it in the microwave part of the spectrum, and it's very, very uniform. It looks exactly the same pretty much every direction of the sky. And there's very little else that you could think would produce something like that other than a Big Bang type explosion. So there's some very strong evidence there. Now, just looking in detail at the first evidence we talked about, the fact that galaxies, there's this relationship between the speed of galaxies and the distance they are away. Well, here we've got the relationship plotted. This is some real galaxy data, and this is kind of looks similar to Hubble's first data. So each cross represents a galaxy. On the x-axis here, we've got their distance in something called megaparsecs. That's just a very large unit of distance that we can use to describe the distances to galaxies. And then the speed in kilometers per second that they're moving away from us. And you can see that we're talking about distant galaxies here, that we haven't plotted any of the relatively nearby galaxies because, as we said, because of gravity, they might end up moving towards us. But these more distant galaxies follow this trend. It's not a brilliant trend. You can see the points are scattered fairly all over the place around this trend line. But there clearly is a trend that the further away the galaxy is, the faster it's moving. And as we said before, that is really serious evidence of an explosion-like event and the expansion of the universe. Okay, so there's a correlation there. And the reason it's not perfect is partly because, well, there are other things that might influence the motion of galaxies, other nearby galaxies via gravity. And also it's incredibly difficult to measure the exact distance of these galaxies. And also their speeds accurately. The redshift data is fine, but there are other things you've got to take into account. It's not quite so simple as it might seem. So there's a lot of error in this measurement, and therefore the conclusions are not as firm as they would be if we could measure really, really precisely what this data was. So that's Hubble's data. One point really about the difference that we talked about before between space existing and the galaxies moving into it, and space expanding. Space expanding from the Big Bang, which created everything, space and time, is kind of what we've got going on here. So I've got 4 galaxies which we're starting off on top of each other. Now this is a bit of a fudge because in the early universe there weren't any galaxies. The first stars didn't form till a fair bit after the Big Bang. But we're going to go with this picture just because it illustrates the point. And so what we're going to do is start the Big Bang off and see these galaxies fly away from each other. So there's going to be little red circles here which represent the expansion of space. And so what you can see is that space expanding is carrying the galaxies away from each other. Okay. So the space doesn't really exist outside these circles. The whole of space is created, expands outwards, carrying the galaxies with it. Okay, so the Big Bang created the whole of space and time. It's been expanding ever since, carrying all the objects in the universe with it. And our final thing to deal with in this video is just thinking about how the universe might end. So there are 3 kind of main scenarios that people talk about. The first one of these is what we call a closed universe. So on this graph here, we've got very simple timeline along the bottom, and then the size of the universe up the side. And so in this picture, the universe, there's a Big Bang is here at the start of time, and the universe expands. But because this universe has got very high mass, so there's a lot of stuff in this universe, that means there's more gravitational attraction. Eventually, gravity will overcome the expansion and cause the universe to collapse back down. That's one possibility. A second possibility, with a universe with a bit less mass in it, sort of medium amount of mass, is that the universe kind of keeps expanding, approaching a fixed size, but you can see the expansion is slowing down. It's getting closer and closer and closer to some size. It never quite gets there, but it also never stops expanding. So that's one of the possibilities with a bit less mass in the universe. And if we have even less mass, then the universe just expands forever. The expansion rate still seems to be slowing down, but it's not going to ever stop. It just gets bigger and bigger and bigger and bigger. So those are the three that are often quoted as being possibilities. And just to be clear, the place we are now is where these things are overlapping, right? We know what, roughly at least, what the local size of our universe is. So whichever of these three is occurring, we can't really tell at the moment, and the reason it's very difficult to tell is, as we've said before, it's extremely difficult to measure the distances to distant galaxies, which is what is used to try and sort of come up with this data. It's incredibly difficult to measure the mass of the universe. We have to count all the material that we can see, and even then it turns out that there's some material we might not be able to see. There's some stuff called dark matter. We don't have time to sort of go into that here, but if you do a Google search for dark matter, you'll see there are some serious problems with us finding all the mass in the universe to start with. So working out how much there is very difficult, and it's just difficult to study the motion of distant galaxies. The Hubble data, the Redshift data is okay, but we can't really tell very easily how the speeds are changing over time, which we might need to do to look at this. And in fact, it turns out that the recent best measurements indicate that none of these are true, and it seems like for some unknown reason the rate of expansion is increasing. So the lines are curving up on this graph instead of flattening out. So this is kind of an open question. Nobody really knows exactly what's going to happen to the universe because the data is very difficult to get hold of, and even when you have got it, it's difficult to interpret. Okay, so that's it for this video. Hopefully it was useful. See you for the next one.